Okay, great. Well, good morning. Thanks again for the invitation to talk about a topic that's I'm passionate about. It's looking into lake sediments to see what kind of information we can find. And in this case, particularly looking at how it helps us to understand how algae are changing in lakes. So, in Muskoka, in Ontario, really across Canada, given the number of lakes we have on the Canadian Shield, we are very, very lucky. We have lakes that are tremendous water quality, have such high intrinsic value, such high ecological value, and that leads to high economic value as well. But at times, these beautiful idyllic places that we enjoy sometimes change. They're often in transition. And at times, they can look something like this. So at times, we can find that the lakes perhaps take on a different color, a different aesthetic quality, when, for example, an algal bloom develops. We're concerned about this, obviously. A number of things we are worried about. First, it changes the aesthetic value. It can reduce the water clarity, for example. All that biomass of algae eventually will die and sink to the bottom of the lake, and as it decomposes, oxygen is used up, which can be a concern for organisms that require oxygen, particularly deep water fish, and cold water fish species. Some algal species at times can produce toxins which are potentially detrimental to human health, the health of organisms. Many produce taste and odor issues as well, particularly when the cells are lysing. And that can affect the taste of water, drinking water, for example, though not a toxin per se, but also the smell of a lake. And some of you may have experienced this kind of thing before. It also affects pocketbooks as well. While property values are a function of many things, including the amount of frontage you have, things like the location, the structural components, it's also been shown, this is a study from Maine, that water quality is a key component of property values. And so water clarity is shown here, for example. And so we're concerned of it from an economic perspective as well. It also gets a fair amount of attention. This was a political cartoon that appeared in the Bracebridge Examiner after the 3 Mile Lake scum in 2005. That attention, of course, can lead to conflict and often to blame, as this individual here is blaming the beavers and changes in water quantity for a particular algal bloom, this species of Aphanizomenon. And it raises questions, of course. You know, if you live on a lake that's experienced an algal bloom, you obviously want to know why it's happening. You'd like to know what the cause is. You'd like to know if it'll happen again. And these kinds of questions are natural. And there are ways then that we can begin to explore and try and answer some of these questions. This is something that I've modified from Steve Carpenter. It's modified by John Small. It's the stool of the approaches to the study of environmental change. So if we did have an algal bloom on a lake, what kind of approach might we take? I modified it a bit. Well, one, we might explore at the local level, the actual lake that had an algal bloom, to see what kind of monitoring data we had. If we were lucky, we might have some data before and after a bloom. We might try and see how things have changed based on inputs of nutrients, for example, or the conditions within a lake itself. We might also be lucky, and we are in Muskoka, where we have a very broad regional monitoring data set. We might be able to take the information from the lake, compare it to other lakes in the region, perhaps lakes that have experienced algal blooms, other lakes that haven't experienced algal blooms. That helps to inform our understanding of what's going on. We might try and model, we might try and understand the factors that may lead to algal blooms. We perhaps try and, if we understand that relationship, we can model the future and determine whether or not we might expect to see algal blooms in the future in a lake and under what conditions. But today I'm going to focus mostly on this, which is the paleo-environmental data. This is the information on lake sediments. It's using the past, an understanding of the past, sometimes in the absence of monitoring data, to help to inform what might happen within a future in a lake. And it's based on a very simple premise that lakes are at the bottom of hills, and over time, and really every minute of every day, they accumulate an archive of environmental information in the sediments. This information accumulates over many, many decades, many hundreds of years, thousands of years since the last glaciation. In some lakes, shallow lakes, there's more sediment at the bottom in the history than there is water on top. There can be meters and meters of information. So we first have to get that information, and there are a variety of ways we can do that, but often we're taking a a sediment core. We can take long cores through the ice. The ice is a very stable platform and pull out meters of sediment at a time. We can use what's called the frigid finger over here, which is essentially a hollow core that's filled with dry ice. And it's very useful for lakes that have actually varved layers like tree rings at the bottom. And some lakes preserve that. Because you can get an annual signal, and you'd like to preserve that annual signal. But most of the time, we're actually just using a gravity core, which is like dropping a straw into milk and capping the top and pulling it out. As you do that, you pull out a history of the lake. We can do this from canoes, as happening here, or boats. And you end up often with 30 to 50 centimeters of material, which in Muskoka can represent 400 years of history for a particular lake. We would then slice that into small sections and date those, and now have a chronology, essentially a library book of the past for a particular lake. And we take that back to the lab, and we start to look at the finer details of what's in the sediment, and it's amazing what's there. The lake really does take information from all parts of different ecosystems, the airshed, the watershed, as well as the lake itself. So from the air, there are records of things like the burning of fossil fuels, the fly ash in the bottom of lakes. We have forest fires that produce charcoal. The charcoal ends up on land and in water in the bottom of lakes, so we can track fires. We can look at vegetational changes in watersheds because the pollen of different species of plants are identifiable. You can look at changes in vegetation. Some contaminants like mercury can travel hundreds, if not thousands of kilometers, and then end up being deposited and leaving a record. This is a lake from Minnesota of an increase in mercury concentrations, total mercury in Lake sediment. Most of what I'll talk about today is what is actually happening in the lake itself. And so some organisms that live in the lake leave a record in lake sediments. For example, these non-biting midges, so the chironomids, their larval stages are actually in lakes and in streams and water. And the head capsules of the chironomids preserve in lake sediment. And these are very, very good indicators of changing oxygen conditions in lakes. Zooplankton important for so many reasons, as we heard in many talks by Dr. Yan. Important grazers, important source of food in lakes. They also, some zooplankton leave a record, and so we can look at changes in zooplankton populations over time. I'm going to talk mostly about algae, and all of these are pictures of diatoms, which will come up later, which are small, siliceous, so they're made of glass, microscopic algae. Beautiful things to see. I encourage you to go and Google diatom art, and there's incredible displays of diatom art. But very, very sensitive indicators of change in lakes. So I'd like to take you on a bit of a tour across the province. I'd like to start in the northwest in Lake of the Woods and talk about some work we've been doing there. We'll make a brief stop up in the Hudson Bay lowlands and talk about some recent work we'll be involved with there, and then try and take that understanding of the types of change we've seen in these places and come back to Muskoka Haliburton, and talk about some of the recent changes we're seeing here. So first, Lake of the Woods. I don't know those of you who've ever had a chance to see Lake of the Woods. It's an incredible place. It's Ontario's 4th largest inland lake. Hydrologically, it's the most complex place I've ever been or worked in. It's got over 14,000 islands. It's really a series of hundreds of bays and lakes connected together. It's on Arctic drainage, so it flows actually north through the Winnipeg River system, the Nelson River into Hudson's Bay. And most of the flow comes through the Rainy River on the south end, which is an international water body. It separates Canada from the US, Ontario and Minnesota. And most of the total phosphorus, so most of the phosphorus which might promote algal blooms, also comes along that river. The management issues will be familiar to you here in Muskoka. It's the same kinds of issues people are interested in, concerned about. Issues concerning development, the management of the fisheries, invasive species, including the spiny water flea, which is now in Lake of the Woods. They have concerns over hydrological management and water levels, how that may affect erosion, climate change. But by far the most dominant issue that people have at the top of mind are these annual blue-green blooms, the cyanobacterial blooms that have been shown to be toxic. But there seems to be this disconnect in Lake of the Woods. There's this perception that blue-green blooms are getting worse. They've increased in intensity, even duration during the summer. But the monitoring data for phosphorus from the Rainy River, where we know 75% of the phosphorus comes from, actually shows quite a significant improvement. That loading, the amount of phosphorus coming in, has actually gone down over time as there's been improvements to the amount of phosphorus coming from paper mills along the Rainy River. So blooms seem to be getting worse, but the loading in this case is actually going down. And actually the phosphorus concentration in the lake is really unchanged or going down slightly as well. But the other catch in the Lake of the Woods in northwestern Ontario is that the region has warmed quite a bit. If you look at the last 60 to 70 years of climate records from across the province, the northwest is actually the region that's warmed the most. It's quite a significant rise in temperature. You can see this is mean annual temperature. This is 1900 until about the present. And it does fluctuate. There are warmer years, even warmer decades. But then, post about 1980, there's been a sudden kind of change in warming in temperature in this part of the province in the northwest. It's had an impact on physical processes in the lakes. We're fortunate that there's a 50-year record of ice, and so this is actually the number of ice-free days, so the number of days of no ice on this particular bay in Lake of the Woods. And that is significantly increased by a month. There's a month longer period without ice now on this bay in Lake of the Woods. So, as someone who deals with lake sediments and paleolimnology, and in a lake where there is some monitoring data, but not really long-term monitoring data, we decided to try and help to inform our understanding of what was going on by looking at the lake sediments. And so we can look at what we would call a reference area of the lake. This is Whitefish Bay, and it's quite interesting because in comes the Rainy River in the south, and it comes up here, and this is where you experience blue-green blooms, right through the center of the lake and up to the north. This is actually hydrologically cut off. There's land here. And so this is very much like a shield lake. This part of the lake doesn't really experience blue-green blooms. It's more like something, and even the look up here is very much like Muskoka. It's shield outcroppings and those kinds of things. But you get blue-green blooms here as you do in Big Stone Bay. So we have this comparative. We have one part of the lake we call a reference area that doesn't have the blooms, and one where it does get blooms annually. The first thing we can look at is actually sediment chlorophyll A concentrations. So chlorophyll A, a photosynthetic pigment that plants have, but also many aquatic groups of algae, like benthic algae, myconic algae, and mosses, and cyanobacteria, which are the blue-greens, have chlorophyll A concentration. And it leaves a marker in sediment. So if we see changes over time, we can infer changes in the amount of chlorophyll A in the water column over time. This is our start then. We started to try and look at chlorophyll A preserved in lake sediment. And quite interestingly, we saw in the reference lake, which is this bottom blue line, essentially, again, there's some variation from year to year, which we'd expect, but in fact, we don't see big changes in chlorophyll A over time. What we see on the impact site is this increase in chlorophyll A, and we looked at multiple impact sites, and I'm going to show you here, that showed the same thing, and the timing was the same. Roughly about the 1980s, we begin to see an increase. And we looked at that relative to measured phosphorus, and there's no relationship, because phosphorus really isn't changing or going down. Where there is a relationship here is the link between chlorophyll A and we have temperature, mean annual temperature here, which is the red line. And we see this, again, this relationship, not much, and then this rise or increase in temperature, which is very strongly correlated to this increase in chlorophyll A. We don't see, maybe some relationship, but really the rise in temperature doesn't cause a rise in chlorophyll A in the reference site, which we wouldn't expect. It's not a part of the lake we have blue-greens, for example. So that was a bit disturbing in some ways, but also surprising. We thought at first we would see some kind of relationship to phosphorus, and ultimately we designed a study to try and to look at those kinds of relationships. We had other information which helped to inform our understanding, and these are these diatoms that I was talking about. These are incredibly beautiful in that every species, or even subspecies, looks different. These are all diatoms that may be living together in some cases. They're all different shapes and sizes. They're ornamented. They're made of glass, so they preserve in lake sediment, so you can see them under a microscope and determine what species you're dealing with. And they're very sensitive to climatic change, and they respond very rapidly to change. And they're sensitive to warming in quite a unique way. Here, I just put two here to show you that what we saw in Lake of the Woods was a change in these kinds of species. You have these very large, heavily silicified, so these are essentially made of thicker glass. They're heavy diatoms called Olitocera. Here's some examples. And this is the same scale to show you we have these very, very small centric or round diatoms, cyclotella, which are much lighter and much more buoyant in water. But as you can imagine, if you have a well-mixed or a cooler water column that keeps essentially these heavy forms up in the light where they need to be to photosynthesize, they can outcompete these smaller forms. So they do well in cooler springs where the lake is well mixed, or a long turnover period, for example. If you get a very warm early spring and a stratification into this warm upper layer and cool deep water, there's nothing in terms of turbulence keeping these heavy diatoms in the water column. They slowly sink out. They're heavy, they sink out. And these smaller, more buoyant forms, just because of their shape and so on, they tend to float more easily. They're more buoyant and they can outcompete these heavier forms. So if you get a shift over time from more of these heavy to more of these light, that suggests a change in the physical structure of the water, which we think may be linked to warming. Let me show you an example. So Whitefish Bay is our reference site. So ultimately we chose it a reference site, and the study looked at changes in phosphorus and expected not to see much in the way of change in diatoms. We saw dramatic changes in diatoms in Whitefish Bay. So again, this is the very light buoyant form, which essentially is not an important part of the diatom assemblage until warming occurs. And then you begin to see a rapid increase in its importance. It begins to outcompete these heavier forms. At the same time, this is in a relative sense, the larger heavy forms tend to drop out. So there's almost a switch and a dominance, which seems to correspond very well with this timing of the warming. So a disconnect in Lake of the Woods? We think in Lake of the Woods that in fact the perception that perhaps the blooms are more intense and they're longer duration may be correct. And I often find that people are very perceptive, especially if they live on a lake and they understand it, and they pick up these kinds of changes. And I think that's correct. That's exactly what's happening. But the mechanism here I don't think is necessarily related to a big impulse of, say, phosphorus concentrations. But that there's a physical change in the lake, which I've just described, which relates to stratification, so the separation of the warm water and the cold water and the timing of that, which is favoring certain types of diatoms and blue-greens. But also something that continues to be an area that we're studying is how changes in temperature and the physics affects how diatoms and blue-greens obtain nutrients and the sources of those nutrients. I can't say anything more on this now because we're still studying this aspect of the chemical change. So let's take that information that we've learned from Lake of the Woods and make a quick stop north. This is a very, very different landscape now. We're in the Hudson Bay lowlands. We're off the shield. These are alkaline waters, higher pH waters. This is an area that includes Polar Bear Provincial Park. We're just, here's Pewanik here. We're just east of Pewanik. And it's an extremely interesting landscape. It's very flat. It is very, very wet. This is the second largest continuous peatland in the world. It's dominated by numbers of ponds, as you can see here, and wetlands, sometimes very large but very shallow ponds. This green one here is very interesting. It looks green, but actually the water is crystal clear. All of that algal biomass is essentially at the bottom of this particularly shallow lake. And a green lake could be next to a blue lake, next to a deep lake. This is a very, very interesting and diverse landscape. Not much, and the vegetation is mostly wetland-dominated vegetation with some black spruce along the margins of major streams and rivers. And so we were up here initially because there was concern over warming. There had been a fish kill that was, the hypothesis was it was perhaps related to thermal stress of these brook char. But there's no monitoring data. And so they were very interested to know if we could get cores from here. Could we learn anything about the past of these particular lakes? it's a bizarre, climatically it's a very unique place in Canada as well. And that's because of, it surrounds the world's largest inland sea, Hudson Bay, which is dominated by ice for most of the year. This is a very, very cold climate. And so that leads to the southernmost extent of continuous permafrost in North America. It comes down quite low because Hudson Bay ice cover essentially is a cooling effect on the local land. And so if you looked at the climate record this was an earlier paper from the 90s, from 1966 to 1995, and this was an early evidence of warming. The area around Hudson's Bay was white here, essentially no change. Temperature hadn't really changed in this area. And then suddenly, particularly the scientists who were studying ice dynamics in Hudson Bay over decades began to see a sudden rapid change. And this is Hokeem and Barber in 2010. So Hudson's Bay has recently undergone a climate regime shift in the mid-1990s. Something seems to happen here climatically in this region. And it's probably a positive feedback. You suddenly have warming in the air reach some tipping point that affects the ice dynamics. And as ice dynamics change, you can have longer periods of warming of the land. And you get this positive feedback cycle. And it really shows up when the records are not that long at airports and so on in the north. But if you look at, say, Churchill, which is one of the longest records, you have essentially some fluctuation in temperature. Obviously, there's going to be interannual variation. And then some kind of change, and this is in mean annual temperature. This is very consistent with the change they were seeing in the sea ice. They weren't looking at the air temperatures, they were looking at the sea ice, which is another measure. There are also on-the-ground observations. We were fortunate enough to stay with Albert Chokamolin at Pewanak Cree in 2009 and 2010. And really unprompted, he began to talk about, he'd lived on the shores of this lake we stayed really for about 60 years. And he talked about things, he'd be coming there with his father initially, the changes that he had seen. So changes in water levels, changes in the amount of aquatic vegetation that he could see, changes in types of fish species that over time he was suddenly catching, like pike, more warm water tolerant fish. And then the interesting story he told was he had walked with his father from Pewanak to the lake, which is about 30 days or something, and had used physical markers in the landscape. When he went to do it with his children about 30 years later, the physical landscapes have changed. Now some of that may be natural change and isostatic rebound, the Earth is recovering from the weight of the ice, but some of it could be related to the types of changes that he had noticed here. So again, we took sediment cores to try and get a history and understanding of these lakes. We looked at diatoms again, and we found the same kinds of changes that we found in Lake of the Woods. We found these buoyant forms, replacing these cold water adapted forms in this case, not the heavy forms, but these cold water adapted forms. The buoyant forms suddenly began to increase around the timing of the temperature change. We see it in another lake, and I can show you multiple lakes where we see the same kinds of changes. So same kinds of changes in the biology, we think responding to the climate changing, but the timing's different, which really improved our confidence that it was related to the temperature change, because the temperature changes differently here. It's about 15 years apart from Lake of the Woods. So we have perhaps some evidence here that there's changes in the ecology and the algae in response to warming. And that may, in Lake of the Woods in particular, where we have severe blue-green blooms, may have an impact on, or at least favor blue-greens in some respects. So let's come to Muskoka Halliburton and look and see whether or not even we see the same kinds of temperature changes. And I thank Jason Kerr. Jason Kerr is a postdoc at Trent. He's part of the Canadian Water Network grant that a number of us are working on. He gave a talk on climate change in the Muskoka, so it was good timing. And he's pulled together information from 6 climate stations within the Muskoka River watershed. Plastic is actually just outside of the watershed. And we can look at the records then, first of all, mean annual temperature, and see whether or not we see these kinds of changes. I should note that the timing does vary depending on the record. So some of our records are shorter from the Dorset Environmental Science Center than some of the longest records at Beatrice. So do we see what we saw at Churchill or even Lake of the Woods, this kind of sudden change, almost a climate tipping point if you wanted to call it that? Do we see that in Muskoka? Is there any evidence of that? And when we just look at the mean annual temperature, the reds are essentially no significant trend. And you look at the mean annual average, so this is this first column in the red. So in this time period, we don't yet, I think, see this kind of distinct warming trend that we've seen perhaps in the northwest and the north part of the province. However, what Jason did note was we do have a significant increase in fall temperature in the shorter records. And the question is whether or not, if you put that in a longer context, it is still a significant increase in temperature. So perhaps you could say, well, we don't yet have a warming that may have an impact on algae. But I think I would argue that perhaps we're seeing early signs, and I'll explain that. If I come back to 3 Mile Lake, so one of the things I was involved with early on in 2006 and 2007, after the scum had formed, was to try and understand the factors that may have contributed to that scum. And one of the conclusions we came to was that 2005, that particular fall, and we know fall is potentially warming, was an extremely unusual year. 2005 was the warmest, driest September, October on record. There had been a drought essentially in late summer into the fall. Just to show you here, this is precipitation. You see 2005, the line is one of the lowest. But when you keep that in line with the fact that the temperature was one of the warmest, then you know it's a very, very dry fall and that particular year. So why does that matter? Well, 2006 and 2007 didn't have scums. They were dominated by blue-green blooms, but I think often 3 Mile may be dominated by blue-green blooms. Some of that could be natural. Dominated but didn't form the scum. And and the water flowed fairly typically in those years. You have a big spring melt. I'd hate to see where the 2013 melt is on this particular site. A big melt. Then you get a drying of water flowing through the system, and then you tend to get a recharge in the fall. You get the fall rains. This scum really dominated through the ends of September and October. If we look at and we model, because we weren't there measuring it, what 2005 water probably looked like through that system, we see that there was essentially no water flowing through the system. So you have a period of the year towards the end of the system when the lake begins to naturally refresh and flush. And some of our earlier accounts from residents was that in that particular year, and it just didn't happen in 2006 and 2007, the outflow was essentially not flowing. So I think part of the contribution of the warmer fall in this case that led to the scum was that you didn't have that recharge of water flowing through 3 Mile Lake that you had normally in most years. So, well, it's still our understanding that the main factors that control algae in lakes are things like nutrient concentrations, the amount of light, available light. Some of this, nutrients in particular, can be controlled by the amount of oxygen in the deep water. So as the oxygen declines, you can actually get higher nutrient concentrations in the water column. I think that meteorological factors are very, very important in determining things like the duration of a bloom. And I think they're important in determining whether or not a bloom develops into a scum, which is much more visible. It's on the surface of a lake. And so I'm somewhat adapting an analogy that I heard Dave Schindler talk about, that if algae are the music that we hear from a radio, it's still true that phosphorus, particularly in lakes on the Canadian Shield, where phosphorus is a limiting nutrient, that phosphorus controls the volume of algae, or the total amount, the biomass of algae during a bloom. And this is still very true. This is one of my favorite graphs, just based on accounts, this is from Minnesota, from people of determining whether or not their lake was not a problem, had a nuisance bloom, severe nuisance, and in Minnesota often very severe nuisance bloom, and equating that to chlorophyll A concentrations and total phosphorus concentrations. And it's still very true that there's a very, very good relationship between phosphorus and how severe your bloom is. So phosphorus still is controlling the volume on that radio. I think other nutrients, especially the amount of nitrogen, but things like light and other factors, or the tuning, they affect what? Species. So you might have a blue-green bloom, but there are different kinds of species that can be dominating that blue-green bloom. I think the tuning is controlled by these other factors. But if I can add to the original analogy I heard, I think that climate is essentially the aerial here. And that in some years, I think the signal is coming in very, very quickly. And I also think that over time, the signal is beginning to become more clear. And I know this analogy will soon not hold water because we don't have these kinds of radios anymore. I'm going to have to adapt it to, I'm going to have to update the technology. But essentially, I think that that's the role that climate's playing here, that in some years, we get a more severe bloom as a result of meteorological conditions. And blues, particularly blue-greens, they like it hot. And that's where I'll stop.
My wife will love what you just said. She's a big proponent of the fact that new water moving in and old water moving out. She figures if lake water gets stale, and the quicker it moves out, the healthier the lake.
Well, yeah, I think to a certain degree that was true in 2005 with the scum, in that there's a natural recharging, reflushing of the lake in the fall, and you know if you don't have that, and you know there's two factors there. Often you're not getting the flow through. It's also quite a sunny period, a drought period, lots of sun. That also favors the development, the warmer temperatures, the development of the blooms themselves. And then if there's a natural recharge and cooler nights and more cloudy days, and then the flushing through essentially, then I think, yes, that can contribute to the decline in a bloom. And it was almost like a switch was turned off in 2010 and that the outflow stopped flowing for a period of time.
Yeah, my perception is that last year was a very dry, warm summer. Do you have data on it?
Yes, certainly it was one of the warmest summers. I should say that when you're looking at the relationships between climate data and the types of things we see ecologically in a lake, we have to be careful the scale we compare those things to. So we could have a very, very warm July, and that may not necessarily lead to a very, very severe bloom in the fall. So we've been looking at recently with Anurani Prasad at Trent University, who's also part of this Canadian Water Network grant, to try and understand what kind of lag in the weather leads to what we see down the road. And once we get to beyond 2 weeks or 3 weeks, there's really not much of a relationship between the climate 3 weeks ago or a month ago. And so it's really that lead-up period when the bloom is developing that's important. So we could have had an unusually warm summer that's driven by a couple of months, but those months don't correspond to the time period when you're seeing the bloom develop. So it's really that period, that critical period when the bloom's developing that we should be looking at. And it's not the same every year, so you can't just say, always look at August temperatures, for example. Yeah.
The new water that's coming in isn't distilled water. Rain has about 5 times the phosphorus concentration of streams and lake waters. So often when you get a big rainfall event, you get a burst of algal growth. So it's not like just dilution. If you look at how algae are processed in lakes, the animal plankton will process the algae about 100 times faster than outflow discharge will. So you can certainly get, so it's actually a little more complicated than like a dilution event, flushing the bathtub. That flushing certainly happens, but it happens on the time scale of years to decades in Muskoka. And the time scale of the control for these events is often much more rapid than that.
Yeah, I mean the point of 3 Mile I wanted to make is that you had a switch turn off, essentially, in that particular period of time when you would normally have some continuous outflow. You don't have any, essentially. You change the nature of, in the immediate term, the flushing of that particular system.
A lot of the lakes in Muskoka, I believe, and I hope it stays that way, do not have a really big blue-green algae problem, but there is anecdotal evidence of more, elephant snot or green slime on the rocks and this sort of thing. Is your data shedding any light on the situation with that type of algae? Is it following the same sort of patterns that you've identified for blue-greens, or do you have information indicating
Yeah.
why some people seem to be seeing more of these other kinds of algae?
Yeah, and I don't know the answer to that. Was Michelle Palmer here? Yeah,
I
no,
saw her earlier.
No, she's not here. But that might come up later in the algal bloom talk. I could say that I'm not sure what Michelle's going to present on, but one of the things that the Toronto office maintains is a tracking these reporting of algae that come in through the ministry. And there's some similarities in that reports tend to come in bunches in particular years, and often for the same kinds of algae. So overall, there's been an increase in reporting of blue-greens, but I believe there's also been an increase in reporting for these kinds of green algae. So it's not something I'm studying directly, but maybe it can come up in discussion later.
I was just wondering, and it may, be relevant for this area in the future, but right now, Lake of the Woods, I'm just wondering, is the Ministry of the Environment looking at strategies to try to counteract some of that blue-green algae? You can't control the temperature, so is there something you can do artificially to try to bring it back in balance?
Yeah, and so it's an international water body, and so and it's interesting that it's quite different in terms of phosphorus levels throughout the lake. So the highest levels are in Minnesota, because that's immediately where the Rainy River drains into water that's actually on the Minnesota side. And there's a very detailed modeling study going on now trying to understand phosphorus sources, because phosphorus is still the volume dial, the control of the volume. And so Minnesota has a very interesting system where they have a trigger system. If phosphorus is below the regional norm, or above the regional norm in chlorophylls, then the lake gets categorized as impaired. And that triggers the detailed modeling study to understand the sources and to run scenarios of what sources you could reduce to try and bring it below. So there's a tremendous amount of work going on. A new IJC reference has just been put forward for Lake of the Woods, and so IJC has now developed a water quality board for understanding water quality in Lake of the Woods. So certainly there's still a lot of interest in looking at phosphorus inputs and getting a handle on what they are.
I just had a question about the series of lakes in northwestern Ontario that the federal government is holding funding on for research. I don't know that, I forget the name.
Experimental lakes area.
That's right.
Yeah.
And I can't exactly say where they are. Have you been involved with any research there, or do you see any hope for, I've heard some things on the news recently that possibly other groups will be picking up the care and investigation going on in the future, and what possible good could come from investigating them in the future?
Well, let me say, part of my master's was doing some work on a couple of lakes in the experimental lakes area. So I had an opportunity to go up and to look at some sediment core information for some of those lakes. And I've since partnered with Dr. Brian Cumming at Queen's to continue to some of that work. Monitoring data is powerful, but it lets you understand potential trends and change. But to really begin to explore potential causes, you really need experimental type data. And what they do at the experimental lakes area, they really don't do anywhere else in the world, which is at the whole lake scale, at the whole ecosystem scale, they run experiments and track the changes in those particular lakes. I'm sure there are others here who are willing to say more and say more. So it's extremely important. It should have been one of those stools, those legs on we have maybe a 5-legged stool that includes experimentation. It's an extremely important part of the process. In terms of its management now, I believe that there's some partnership. I've just read what other people have probably read. Maybe Terry, you would have some words on that. That there's some partnership to have it going for another year between the Ontario government and the Manitoba provincial government and ISSD, but whether or not, that's I think just potentially a stopgap approach until they can have some kind of longer term form, unless someone else here knows anything more than that. But it's an extremely important part. It's informed so much in the way of policy. The understanding that phosphorus was a key nutrient in driving biomass of algae came from those kinds of experiments at the experimental lakes area. And perhaps it's a picture you've seen of a lake divided in two, where one side is very green and one's not, and the side that's green is the side that it additionally added the phosphorus to. So it's very important not only for the science, but for informing the public, and it's a great, tremendous educational tool as well to see those kinds of pictures. Norm?
Yeah, the only thing I personally would like to add to that is everything Andrew said is true, but I would add to that there's at least 5 experiments that are going on in the ELA now that are vital to the future management of lakes here. So it's not just a historical contribution. So they're doing work on, there's a big nanosilver experiment that's planned. No one knows the influence of nanosilver, and its use is growing industrially. They've had a big aquaculture experiment. We have all of our net pen aquaculture facilities out in Churchill Bay. They have 2 climate change experiments underway. One is looking at drought effects, so they pulled a lot of the water out of one lake. They've changed the sort of how lakes are connected. They're also doing a flooding experiment, so they're doing both flooding and desiccation experiments at ELA. They're also doing experiments, whole lake experiments on hormone analogs. Estrogen, estradiol, I think, has been added to a whole lake. So if you ever hear anyone say, ELA has done great work in the past, but what's it doing for us these days? There's a huge amount of very important work on emerging stressors that's going on at the experimental lakes area. So it actually is vitally important that we keep things going.
Both environment, what would you say are the top 3 contributors to phosphorus levels that are related to human activity? Something that we would have control over.
Well, I would say the top 3 are probably the removal of trees is very important, I think, and vegetation, particularly around shorelines. I think that can have an impact on the movement of phosphorus. Vegetation takes up a lot of that phosphorus, and also it creates and reduces erosion, creates a stability to the soil. I think that, for example, we put a lot of phosphorus into septic systems. I think septic systems, although they're, it's a science that's continuing to evolve in understanding and trying to understand how we properly measure the movement of phosphorus. I think there's still evidence in some, there's evidence that there's movement of phosphorus in septic systems. I think those 2 are important. Trying to think of Norm, do you want to jump in a third natural one? I would say one possibility is that, or maybe Neil, that a lot of phosphorus to some of our lakes comes from the lake sediments themselves. And as you lose oxygen in the deep water of lakes, you can see potentially an increase in phosphorus to the water column. And so perhaps factors that are changing oxygen levels in lakes could have an impact. I don't have a set example for you here.
The Yellowfish program in a nutshell is currently underway in Muskoka, specifically in Huntsville, Bracebridge, and Gravenhurst. It's an awareness program where volunteers go and paint a little yellow fish by the stormwater catchment basins to remind people that everything that goes down those basins typically ends up directly in a river or a lake. In some cases it is treated, but not fully. And so basically if you're washing your car with a bunch of detergent and that's all running down your driveway, it's going to go into a catchment basin and straight into the river. So there you're going to get some nutrient loading that maybe you weren't thinking about. I've personally heard stories where people have changed the oil in their car and just walked to the end of their driveway and dumped it right down the stormwater catchment basin. So I mean, and there's a lot milder influences on that, but those are some harsh ones. And so the program is designed to raise awareness so people don't do that sort of thing. And maybe we just do simple things like making sure our cars are properly tuned, and we're not putting a whole lot of stuff on our grass that just runs off and goes down these drains.
Also mentioned phosphorus in rain. What's the contribution of that? How great is it, and how's the phosphorus getting there?
Yeah, so the phosphorus from rain, the contribution may vary on a relative sense from lake to lake, because we often categorize that component as the part that's falling directly onto the lake's surface. And so if a lake, imagine, has a very large watershed but a small lake area, the contribution is probably less than a lake that has a very small watershed in a broad area. But the phosphorus concentration can be, in some lakes, from rain, the primary source of phosphorus to a lake, and it's things like dissolved phosphorus, but particulate forms, things like dust and so on, and pollen, these kinds of things that rain directly onto the surface of the lake contribute phosphorus in a natural sense. Now, I should say, before Norm adds to that, I should say, Honeywell, I should say that, you know, we do track, we have long-term records of phosphorus concentration from rain, a number of monitoring stations in Dorset that are maintained by the Dorset Environmental Science Center. There are changes, again, from year to year, decade to decade, but when you look at the longer-term trend, we're not seeing any long-term trend in phosphorus concentrations or the load coming from the rain.
Do you see that there will be a measurable increase in the phosphorus results, say spring turnover, because of the flooding that will happen?
That's a very good question. I'm not 100%, and I'm not sure whether or not it's something I could generalize to all lakes. A lot of it will depend on the concentration, the load coming in through this floodwater relative to other sources coming into a particular lake. It's possible we may have higher phosphorus concentrations in some systems as a result of the flooding of areas, expansion of wetlands and those kinds of things. But I don't know. It's certainly something that we're going to be tracking this year. And you know, we've had two very strange years back to back, which helps to inform our understanding of, say, the impact of changing climate. Because we had such, one of the things with warming is this, one, it's not a gradual increase in change. One of the things that comes with it is this increased variability. And so we have here an opportunity in a very warm, unusual snowmelt, early ice-off year versus what we're experiencing this year to really contrast, to see in those extremes what we see. And so we'll be looking for it, but I wouldn't want to make a prediction.
Just a bit of a follow-up to your second point on septic systems, because people here are often concerned about their own sewage treatment systems and its ability to contain nutrients and bacteria. I'm involved in a few assignments where two lakes in southeastern Ontario, one on Manitoulin Island and another lake in southeastern Ontario, where we're parts of plans of subdivisions or severances have been approved subject to using phosphorus removal technology that the Ministry of Environment Standards branch in Toronto have viewed initially as having potential to reduce phosphorus. These plans of subdivisions and severances, their systems will have to be monitored for a period of time. And if in fact the Ministry of Environment determines that the specific phosphorus removal technologies are adequate, then the balance of the severances or the plans of subdivision can proceed. The ultimate objective is for one or more of these technologies to find themselves eventually into the Ontario Building Code as being acceptable phosphorus removal technologies for individual lots and systems. I don't want to give you the impression that this is all happening immediately. It's taken a long time to get to this point, and it's going to take a long time to work through the system. The point I want to leave you with is that there are some initiatives on this second point that Andrew has mentioned that are currently being looked at in a more fulsome way than they have been in the past.
You also mentioned nitrates as another nutrient. Can you comment further on how they play
I talked
into the
about
water
it as a tuner for these Canadian shield lakes in particular. These lakes, we've determined, are limited by phosphorus. But what the nitrogen in the system can determine whether or not you have the types of blue-green species that can directly fix nitrogen from the air. So if they're limited by nitrogen, there's not enough nitrogen in the system, they can get the nitrogen they need if they have enough phosphorus, essentially. And that just has an impact on the types of species you see versus other species. I should say that, you know, in terms of whether or not a species is toxic or not, you can have both nitrogen fixing versus non-nitrogen fixing species. So more the point that, there's been a debate, for example, in Lake Winnipeg, as to whether or not you should be controlling phosphorus versus nitrogen, or both. And the argument, this is when this analogy I think came forward by Schindler, that ultimately the control in the volume is still phosphorus. And the nitrogen will control your relative species, but ultimately the focus on a particular system should be on phosphorus. So there are other factors that control the types of species you get. But and in what we tend to have in, for example, 3 Mile Lake, is what we have is we have these at times, sometimes both the nitrogen and the non-nitrogen fixing species from the app.
I think Dr. Yan mentioned the nanosilver getting systems and stuff like that. Now, the nanosilver industry, I think, is something, we love everything that's got nanosilver. Now we know, some of the issues that it is causing. Is there anything at work to say for that feedback to like that information to go back to the nanosilver industry? And do we have any anything that can weigh on them to reduce the damages?
Well, I think...
Before you go, can you just, for people that may not know what nanosilver is in?
Yeah, and I'm not an expert on it, but maybe enormous.
No, I'm not, but it's never stopped me before. It is kind of a, I don't know, it's thought of as a new wonder product, and it's the basis of this whole nanotechnology and manufacturing industry. It's most beneficial so far at bandages. Bandages made of nanosilver have almost magical healing properties. And I think it was 2 years ago that the sale of nanosilver bandages in hospitals exceeded over $1 billion. And so it's a huge, huge industry. And so it seems to be uniquely toxic to bacteria. But the problem with it is that silver itself, we know dissolved silver is quite toxic. But this is not dissolved silver. So this is microparticles, tiny, tiny particles, which essentially don't dissolve. And so the toxicological issues, as much as I know, relate to the erosion of cell membranes and things like that. But I'm not an expert. What I do know, I'm absolutely not an expert, so don't quote me. My wife, if she was in the audience, would be laughing right now, because she knows it's never stopped me before. And, is that the experiment that's planned for ELA reflects the seriousness of the potential issue. And I think it's an $800,000 planned experiment to look at the impacts of nanosilver at the scale of whole ecosystems. And hopefully this new announcement, or at least the short-term continuing funding of ELA, will allow that work to go ahead. As to feedback, now here this is a complete speculation. I suspect that industry is quite involved in that experiment because much of the work that has gone on at ELA over the last several years, the user groups, both industrial and otherwise, do get involved because they understand that to move forward, governments ultimately want information, real information. And this is a proven fabulous way to get real information on. So ELA does two things. Andrew's right, there should be a fifth leg in the stool, experimentation. The other thing that ELA does that's incredible is allow you to set targets, real targets, that reflect ecosystem scale risk. And you can't get that. So that's the second critical thing, or the third thing is time series. But the second critical thing that ELA does is allow you to set targets, in this case for nanosilver loading or concentrations, that reflect ecosystem scale risk. And we can't do that any other place than in ELA. Right?
We reside in the poor man's end of Muskoka at Sparrow Lake. That's $5 million south of Port Carlin. our watershed consists of everything north of the moraine, plus that little market garden called Holland Marsh. And the blue-green algae problem last year was severe enough that most people could not use the lake for swimming. And so the federal government has just recently announced that they are going to spend another $29 million on the Lake Simcoe southeastern Georgian Bay water quality area. And I'm wondering if you, Andrew, and Dr. Norman can suggest how we can assure that that money is spent scientifically rather than bureaucratically.
I can probably answer that one because applications were put in quite a while ago, they should have been announcing. And it was all on a project by project with defined objectives and deliverables.
Right, peer reviewed by other scientists.
All peer reviewed.
But I think there's two phases to that. It's a second phase, but I think there's two phases to the second phase. I think the first phase was focused on Georgian Bay. You're talking about the Simcoe Georgian Bay. And the second phase, we focus more on the Simcoe watershed. Maybe Michelle's here now to confirm that. But
Yeah, so the first phase will focus a fair bit on research and a lot on Georgian Bay, but I'm not sure if there's been determined that there's going to be a separation between Simcoe versus Georgian Bay in either years.
But so there are proposals submitted by mostly academic scientists that are going through a peer review process as we speak, and then they'll move forward. Those that are approved and have there's funding available move forward with some of the science.
I'm here representing Cashy Lake. And I think our property values just went up. I thought we were 5 million south of. We're a little bit north of Sparrow. The question I have is there a publicly available database that we could, that lake stewards could go to see if their lakes have been evaluated?
Yeah, I mean there are a number that are available even online now, and so for example for phosphorus data, I would explore whether or not your lake.
I've got all the phosphorus.
Through the Lake Partner program?
Or is the sediment studies?
Oh, so not that I know of as a publicly available database. You could contact me and I could let you know. I know this region very well for the sediment work. Across Ontario, there's something, I did a tally recently, something like 500 or 600 lakes that we have this kind of ecological paleo data now. So and much of that is focused heavily in Muskoka Haliburton. We have maybe 150 lakes, so we have some information on the ecological side.
Thank you.
So I could explore that,
Yeah.
I just wanted to come back to the nanosilver for a minute, because Norm had mentioned one very valuable application of it in treating human health. But the really big market for these nanosilver things are they're putting it into t-shirts, underwear, socks, so we all smell nicer. What this means is there's a real diffuse spread on the landscape. Every sewage plant is putting nanosilver out in the environment. So that makes it a very widespread problem and a consumer problem, and so it's all the more reason to investigate it. And then coming back to the other work that Norm mentioned at ELA was pharmaceuticals and microcontaminants, things like the remnants of our hormones that we put down in the sewage, of the pills that we take, and those are very poorly understood as well. The best way to look at those is the whole system type experiments that Norm and Andrew mentioned.
There's been some amounts of money mentioned in some of the questions and some of the answers, the costs of various things, and to put some things into perspective. The stated reason the federal government was using to close the experimental lakes area was its operating cost. And there are two numbers that are reported. One's $2 million a year and the other $600,000. The $2 million is the cost of a number of salaries of scientists who presumably weren't going to be shot. The $600,000 is the actual cost of the things they do to keep the thing running. You put those kind of costs in the context of the value to the economy of the nanosilver industry, or some of the single experiments that are being funded, you get some perspective on how much money is involved and where it could best be used.
So what Peter was saying, for the people in the back that couldn't hear that, is basically the reason the government gave for closing down ELA was its cost. $2 million, which was for scientists. Peter said they probably weren't shot, so they're probably still around someplace. And $600,000 basically for the operation of that facility, which isn't very much when you look at the millions of dollars, probably billions of dollars going into the nanosilver industry. So the cost benefit.
Yeah. Some of those scientists have received effective notices, meaning they may or may not be laid off.
Terry.
Unless we're all excited about this reprieve, the reason this fifth leg works mostly, in my understanding, is you can count on multi-year type of whole lake experiments. That requires a lot of planning, a lot of students, a lot of time in lake to make this stuff, which is whole lake experiments, happen. So 1 year reprieve with no dollars attached to it yet. Let's not be too comfortable with the fact. It's a positive development that we hear someone's talking about it. But if you happen to vote for anyone who's like the Treasury Board president, just saying. I haven't heard anything from the federal government, so it's worth hearing what they've got to say about it.
DFO did have speak.
Oh, what did they say?
They were saying they were leading the discussions.
So back to my point, I haven't heard anything about any money coming, and 1 year is interesting, but it's not really an answer yet. So I'd encourage you all to continue to push whoever you are inclined to speak to about this, to how you're feeling about the value of that to us as Canadians.